Hello everyone, welcome to this lecture. So just to recall, in the last lecture we had introduced the random oracle model.
So, in this lecture we will continue our discussion on random oracle model. Specifically, we will see constructions of several cryptographic primitives based on hash functions whose security proof we cannot just prove based on the standard properties of the hash functions, and by standard properties I mean the collision resistance property. And it turns out that the proofs for those cryptographic constructions which we are going to see in this lecture can be completed only in the random oracle model.
So before we proceed, let us first argue whether the random oracle methodology is sound or not, because as you remember, in the random oracle model we are making very strong assumptions about the underlying hash functions, right. Namely, we assume that the underlying hash function behaves like a truly random function with no entity in the system which uses that cryptographic primitive have access to that oracle. Everyone makes, if someone wants to evaluate that underlying oracle on some input of its choice, then it has to make oracle call, and it is not allowed to see the internal details of the underlying oracle, which is far away from the reality, because in reality when we instantiate a cryptographic construction based on hash function, then we have to select some candidate hash function, and everyone in the system who is using that primitive will have access to the code of that hash function. So that brings us to the debate whether the random oracle methodology is sound or not. And now it turns out that in cryptography we have two school of thoughts here. We have one group which says that the random oracle methodology is indeed useful, whereas the another group is against it. So let us see first the objections to the random oracle model. So as I said earlier, that the security of any cryptographic primitive pi, say pi, which is based on random oracle model, not only depends upon the random choice of the parties who are using that primitive, but also on the random choice of the underlying oracle H. That means that the primitive pi need not be secure when actually we go for the deployment of the primitive pi by instantiating that oracle H by some specific real world hash function, because it so turns out that no concrete hash function, say the SHA functions and the MD5 functions and so on, can behave like a random oracle. First of all, none of these hash functions behave like a truly random function, and even if we so assume that they behave like a truly random function, we cannot prevent the adversary to see into the code of the underlying hash function. It will know the full details of the underlying hash function, whereas the security proof that we give in the random oracle model, it depends upon what specific underlying random oracle we are using during the instantiation of the primitive pi. Whereas the other school of thought which is in the support for random oracle model is as follows. So it turns out that there are several cryptographic primitives which are highly efficient, and we will see some of the examples of such primitives in this lecture, and later on we will see that most of the practical public key cryptographic primitives or public key crypto systems, their security they use hash functions, and their security can be proved only if we go in the random oracle model. We cannot prove the security of those public key cryptographic primitives based on hash function just using the collision resistance or the standard properties of the hash functions, right. So the support for the random oracle model based proof is that a security proof that we give in the random oracle model, it gives you the confidence that as far as the design principle of that cryptographic primitive is concerned, it's sound. The only weakness in the primitive when we actually deploy that primitive could be due to the underlying instantiation of the hash function. As a design principle of that primitive pi which uses the hash function as a random oracle, there is absolutely no flaw. So that is the support that we give for a proof that we could come up for a proof that is there in the random oracle model. Also it turns out that for almost all the cryptographic primitives whose proof are there in the random oracle model, we have obtained no successful real world attacks when we actually instantiate the hash functions by some real world hash functions. So that is another arguments in the support of the random oracle model based proof. And the final argument which is there in the support of the random oracle model based proof is that a proof in this a proof of security of some cryptographic primitive in the random oracle model is far better than no proof at all. That means, imagine you design a primitive pi based on some hash function, and for that you have absolutely no proof at all. Whereas, you have the proof for the same primitive, but in a very idealized setting, namely say random oracle model, then you will be feeling confidence that indeed if I instantiate this primitive pi by instantiating the underlying hash function, then the only flaw that could be there might be due to the weaknesses in the underlying instantiation of the hash function, and then what you can think of? You can think of coming up with a better replacement or a better instantiation of that hash function instead of changing the design of the whole primitive pi. So, that is a very strong argument in the support for a proof that is given in the random oracle model. And as I said, you have two classes of two types of groups here. One group hates proofs given in the random oracle model, whereas other group supports proofs given in the random oracle model. So, as a design principle, we should always try to design schemes whose proofs are not in the random oracle model. Namely, we should try to design schemes which uses hash function whose security can be proved just on the standard properties of the hash function, namely the collision resistance property. But if at all it turns out that we cannot give a proof just based on the standard properties, but we can go give proofs for the we can give proofs in the random oracle model, then we should go for proofs in the random oracle model, provided that the construction that we are giving are highly efficient. So, basically you have trade off. You have a trade off in the sense that if you have a construction based on hash function and they are highly efficient, but with no proof, whereas you have another construction for the same primitive with a proof in the standard model, but highly inefficient, then for the sake of efficiency we can prefer to go for the scheme based on the hash function whose proof is available in the random oracle model. So, let us see some cryptographic primitives which we can design using hash functions, for which the security proof can be given only in the random oracle model. And the primitive that we are going to see here is what we call as commitment schemes, and it is basically a two party primitive involving a sender and a receiver, and it basically consists, when we say that we have a commitment scheme, it consists of two protocols or two phases, a commitment phase and an opening phase. So, what happens in the commitment phase? In the commitment phase, sender has a message which is private and known only to the sender, which we denote by say little m, which can be a bit string of some arbitrary length. And in the commitment phase, basically sender wants to commit the message to the receiver. So, you can imagine that in the commitment phase, the sender computes a fixed length commitment which we denote by C for the message m, and this commitment C is given to the receiver R. So, you can imagine that this commitment C is like a sealed envelope or a sealed box inside which the sender has put the message m and given it to the receiver R. And the security property that we require from this commitment phase is that if the sender is honest and if the receiver is corrupt, then by looking into the commitment C or by looking into the envelope C or in the box C, the receiver cannot find out what exactly is the message m which has been committed in the commitment C. So, that is the commitment phase of commitment phase of a commitment scheme. Now, let us see what happens in the opening phase. So, imagine receiver has received a commitment of some unknown message available with the sender. In the opening phase, the sender provides or reveals the opening information to the receiver, using which the receiver opens the commitment and the receiver verifies whether the opening information is correct or not, and based on that it either accepts or rejects the revealed message that is there in the commitment. And the security property that we require from the opening phase is as follows. Now, we consider a corrupt sender and an honest sender and an honest receiver. So, remember, for the hiding property we considered an honest sender and a corrupt receiver, but when we are considering the binding property with respect to the opening phase, we consider the case when the sender could be corrupt and the receiver is honest. So, what exactly the binding property means is that a corrupt sender should not be able to open a commitment C in two different ways. What it means is that it should not be possible for a corrupt sender to commit a message say m during the commitment phase and later on provide a revealing information which ends up opening that commitment C to another message m dash. That means, once sender has fixed his commitment and he has decided what exactly to commit, later during the opening phase he should not be able to change his mind. So, now let us see how exactly we can design commitment schemes using hash functions. I stress that this is not the only way by which we can design a commitment schemes. Later on, when we will be discussing the number theoretic hardness assumptions, we will see how we can design commitment schemes based on cryptographic hardness assumptions based on number theoretic problems. But right now we are trying to give a scheme based on a hash function. So, imagine you are given a collision resistant hash function h, and the commit phase or the commitment phase for the commitment scheme that we are going to design is as follows. So, the message that the sender wants to commit is some message m. To commit this message, what the sender does, it picks a randomness of some suitable size, which is denoted by s. So, basically s is a uniformly random string of size little n bits, where n is some security parameter, and the commitment of the message m is computed as follows. Basically, sender evaluates or computes the hash of the input message concatenated with the randomness, which we denote as c, and we call this protocol as protocol com with respect to the input m and the randomness s. And the commitment information c is given to the receiver. That is a commit phase. During the opening phase, the receiver has a commitment already available to it, and it wants to now see what exactly it corresponds to based on the opening information which the sender is going to provide. So, what sender provides in the opening phase is the message comma randomness, which it might have used in the commit phase to commit the message m in the commitment c, and once the message comma randomness comes to the receiver, what the receiver basically does, it recomputes the commitment by hashing the input message concatenated with randomness and checks whether the recomputed commitment matches the commitment c, which the receiver already has received during the commit phase. If it matches, then the output is 1, that means accept the message m, whereas if the recomputed commitment does not match the existing commitment c, then the receiver rejects the message m and output 0. So, that is a very simple construction of a commitment scheme based on a collision resistant hash function. To commit a message, concatenate a message with some appropriate randomness and hash it. To open the message, you basically open the message or you reveal the message along with the randomness which you have used to compute the commitment. Now, what we are going to prove is that this commitment scheme that we have designed here satisfies the hiding property and the binding property. And before we go into the proof, let us formally define what exactly we mean by the hiding property and the binding property in the context of a commitment scheme. So, remember, the hiding property informally requires that if the sender is honest and the receiver is corrupt, then by looking into the commitment c, the receiver should not be able to identify or learn what exactly is the message m which has been committed in the commitment c. And this is modeled by an experiment which we call as the hiding experiment. So, the rules of the hiding experiment are as follows. So, we have the description of a publicly known commitment algorithm, right, which is going to be used by the sender to commit some message, and we have an adversary A who wants to basically learn the value of the message which has been committed in a commitment, right, even by knowing the description of the algorithm com. So, the game is played between the adversary and the experiment or a challenger, and what the rules of the game are as follows. So, basically the adversary submits a pair of messages m0 comma m1, and the challenger basically does the following. It randomly decides one of these two messages by tossing a fair coin, and once it has decided what message to commit, it picks a randomness of appropriate size as per the commitment algorithm com, and it commits that selected message mb under the randomness s, right. And now the challenge for the adversary is to identify whether the C star is a commitment of the message m0 or whether C star is a commitment of the message m1. So, what this basically experiment models is that if the adversary is sitting in between, if the receiver is corrupt, right, then based on the commitment that it sees from an honest sender, it should not be able to distinguish apart whether it is seeing a commitment of m0 or whether it is seeing a commitment of m1, where the receiver is given the power that it already knows that the commitment could be either the commitment of m0 or m1. So, the output of the adversary is a bit, namely whether it feels the commitment C star is a commitment of m0 or m1, And our security definition is as follows. We say that the output of the experiment is 1 or the adversary has won the game if it could correctly identify the message which has been committed in C star, namely its output B dash is equal to B. And we say that formally a commitment algorithm COM satisfies the hiding property if for every polytime adversary participating in this experiment there is some negligible function such that the probability that adversary can win the hiding experiment is upper bounded by half plus the negligible quantity. And another way to put the same condition is that the distinguishing advantage of the adversary should be upper bounded by some negligible function. That means it does not matter whether the commitment is for message M1 or whether the commitment C star is for the message M0. In both the cases the response of the adversary is almost identical except with some negligible function. And in both the definitions the probability is taken over the random choice of the bit B and the randomness S and the random choice of the adversary with which it could decide the message pair M0 comma M1. So, on a very high level this indistinguishability based definition of commitment might look like the indistinguishability based definition of encryption schemes that we have seen. The only difference here is that we do not deal with any keys here, right. So, that is why we do not have any training phase and post training phase and so on. The goal of the adversary is basically to just distinguish apart a commitment of M0 from a commitment of M1. Now, let us formally define the binding property, and remember informally the binding property demands that if the sender is corrupt and the receiver is honest, then it should not be possible for a corrupt sender to open an existing commitment C via two different messages. And this is simply modeled by an experiment where the adversary's goal is to come up with a commitment C and a pair of message comma randomness, where the first message comma randomness is M comma S and the second message comma randomness pair is M star comma S star, such that the commitment of the message comma randomness the commitment of the message M with the randomness S and the commitment of the message M star and the randomness S star are same, namely C, even though the message M and message M star are different. If that is the case, then we say that the adversary has won the game. So, when we say that the sender wants to break the binding property, its goal is basically to come up with some message M and the corresponding randomness S and another message say M star different from M and an appropriate randomness S star, such that when you commit the message M with the randomness S, you obtain the commitment C, as well as when you commit the message M star with the randomness S star, you also again obtain the commitment C. If that is the case, if that is possible, then what the corrupt sender can do is during the commit phase it could commit a message M with some randomness S, but when it comes to reveal the message which it has committed in C, it can change its mind and say I have committed M star by showing the appropriate randomness S star. What we want from a commitment scheme satisfying the binding property is that the probability that a computationally bounded or computationally corrupted S is able to come up with such M comma S and M star comma S star is upper bounded by some negligible function. So, formally we say that a commitment scheme has the binding property if for every polytime adversary A participating in this experiment there is a negligible function such that the adversary can win the game or it can break the binding property is upper bounded by some negligible probability. Notice that we are not putting in this definition that the success probability of the adversary should be upper bounded by half plus negligible, because here the goal of the adversary is not to distinguish a commitment of M0 from a commitment of M1. His goal is to basically come up with a pair of colliding message comma randomness with both of which could give you the same commitment. And there is always a non-zero guessing strategy, there is always a guessing strategy by the adversary where the adversary could guess M comma S and M star comma S star, which indeed gives you the same commitment C as per the commitment algorithm, and the success probability of this guessing adversary is non-zero. So, that is why in the definition the best we can hope for is that the success probability of any adversary coming up with a bad M comma S and a bad M star comma S star giving the same commitment C is upper bounded by some negligible quantity. So, now let us come back to the hash function based commitment scheme that we have designed, and what we are now going to formally prove is that commitment scheme satisfies the binding property and the hiding property. So, the binding property will simply be based on the collision resistance property of the underlying hash function. So, assume we are given a collision resistant hash function h. Here is how we have constructed our commitment scheme. So, to commit a message m with some randomness s, basically you have to compute the hash value on the input m concatenated with s. And we can formally prove that if the underlying hash function is collision resistant, then indeed the algorithm com that we have defined here has the binding property. Namely, what we can formally prove is that any polytime adversary who can break the binding property with a significant probability, with almost the same probability, it can be used to find out a collision in the underlying hash function with a significant probability, but that is a contradiction to the assumption that our hash function is collision resistant. More formally, assume we have an adversary, a polytime adversary who can break the binding property against the commitment scheme that we have designed. Using that adversary, we can show another adversary which can find a collision in the underlying hash function. So, what this adversary a call does is it invokes the existing algorithm a bind, which can break the binding property, and basically the adversary who can break the binding property, he comes up with this set of triplet. Namely, it comes up with a commitment C, a message comma randomness m comma s, and another message randomness m star comma s star. And what this adversary a call does is it outputs a pair of collision, namely m concatenated with s and m star concatenated with s star. And it turns out that if indeed the adversary a bind has broken the binding property, namely the triplet that he has produced breaks the binding property, that means m comma s as well as m star comma s star gives you the same commitment C as per the algorithm com, then indeed the inputs m concatenated with s and the inputs m star concatenated with s star constitutes a collision for the underlying hash function. That means what we can say is that the probability that our collision finder wins the collision resistant experiment is exactly the same with which our adversary who can break the binding property can break the binding experiment. But since we are assuming that our hash function is collision resistant, then we know that the quantity on your left hand side is some negligible function, right. No polytime adversary could come up with a collision in polynomial amount of time. That means this adversary a call does not exist, and that automatically means that the adversary a bind also does not exist. That means only with negligible probability the so called adversary a binding that we have defined exists. It cannot break the binding property with significant probability. Now, let us prove the hiding property of the commitment scheme that we have designed, and it turns out that just by using the standard properties of the hash function we cannot prove the hiding property. But interestingly, we can prove that if we instantiate this commitment scheme in the random oracle model, then in the random oracle model we can prove that this commitment scheme satisfies the hiding property. So, let us go into the detail. Now, since we are going into the random oracle model, we have to modify the hiding experiment. So, remember in the hiding experiment the rules of the game were as follows. The adversary simply throws a pair of messages m0 comma m1 and one of them is randomly committed, and the challenge for the adversary was to identify whether it is seeing a commitment of m0 or whether it is seeing a commitment of m1. But now, since we are going to instantiate the commitment using a hash function which is taken in the random oracle model, and in the random oracle model each entity in the system is going to have oracle access to the function h, we have to incorporate the oracle access to this oracle h in the experiment. So, the modified experiment is as follows. So, the adversary basically submits a pair of messages and the challenger or the experiment decides one of the messages to commit randomly. So, it decides a suitable randomness once it has decided what message to commit, and now it throws the commitment of that message as per the COM algorithm, and to commit that message MB, basically this challenger has to evaluate H of MB concatenated with S. But since we are assuming that we are in the random oracle model, this hash function is this output H of MB concatenated with S is obtained by the experiment making an oracle call to the oracle H on the input MB concatenated with S. And as per the rules of the random oracle model, adversary A is not allowed to see the oracle call that this experiment has made to the oracle H. Now, since we are in the random oracle model, this adversary A is also allowed to make polynomial number of oracle queries to this oracle H on any input of its choice, and then finally it outputs whether it has seen a commitment of the message M0 or whether it has seen a commitment of message M1. I stress here that in this whole experiment the function h is a random oracle with neither the experiment nor the adversary having access to the code of this oracle h. So, since we want to now prove that what is the probability that adversary A could significantly output B dash equal to 1, since we are in the random oracle model, we have to basically argue that what is the probability that adversary has made oracle query with inputs of the form something concatenated with the randomness S. So, remember that the commitment C star is the output of the oracle H on some message MB, where MB could be either M0 or M1, which is already known to the adversary A, because adversary itself has thrown that pair of messages. What the adversary does not know is the other part of the input which has been used to compute the commitment C star, namely it does not know the value of the randomness S, and since the randomness S is a uniformly random value, the probability that adversary A makes an H query of this form, namely H query where the input of the query is something concatenated with the randomness H S which has been used by the challenger, is maximum 1 over 2 to the power n. And conditioned on the event that adversary has not made any query of this form, namely a query H query of the form something concatenated with S, the value of C star is going to be a uniformly random value from the viewpoint of the adversary, and it does not reveal anything whether it corresponds to the H output or H value for the message M0 or for the message M1. That means with almost same probability from the viewpoint of the adversary, it could be a commitment of M0 or it could be a commitment of M1. So, now you can see that as soon as we take this whole construction, this simple construction based on the hash function and take it to the random oracle model, we can very conveniently give a proof that indeed this construction satisfies the hiding property. But if we do not take this construction in the random oracle model, we cannot complete the proof, security proof for the hiding property just based on the standard properties of the hash function. So, now let us see some other primitives which we can use, which we can design based on hash functions whose property we can, whose proof we can give only in the random oracle model, and this primitive is what we call as key derivation function, and later on when we will be discussing public key cryptography, we will be extensively encountering this primitive. So, what exactly is the goal of key derivation function? So, the scenario is as follows: imagine we have two parties, say sender and a receiver, and they have some pre-shared data which is highly unpredictable. And they need not be, that highly unpredictable pre-shared data need not be in the binary form, it need not be a binary string, and not only that, it need not be a uniformly random bit string. For example, you can imagine that S and R might have pre-shared a common password consisting of 28 characters, where all the characters are uppercase letters, namely they belong to the set big A to big Z, and each of the characters of the password could be is any of the characters in the set A to Z with equal probability and random with uniform probability. So, that is the scenario, and the goal here is basically sender and receiver locally want to apply some function on their pre-shared data M and derive a random secret key. For example, they might be interested to derive an 128-bit uniformly random AES key from the pre-shared data M, which is highly unpredictable and not known to anyone except the sender and the receiver. I stress here the goal is to do that by locally applying some publicly known function, right. Sender and receiver do not want to interact, they just want to apply some function on the pre-shared data M and want to derive some random secret key. It turns out that if sender and receiver applies some ad hoc mapping or ad hoc function to the pre-shared data, then the resultant output need not be uniformly random bit string. For example, let us take the case where both sender and receiver takes the ASCII bit representation of the first 16 characters of M. Why 16 characters? Because the ASCII representation of each character will be 8 bits, and since the goal of the sender and the receiver is to derive a 128-bit key, it suffices for the sender and the receiver to just concentrate on the first 16 characters of their common password and convert the 16 characters into the ASCII representation and take that to be the resultant AES key. And intuitively you might feel that since the password consists of uniformly random uppercase characters. When those uppercase characters are converted into their ASCII representation, the corresponding binary representation also will be uniformly random. But it turns out that this ad hoc mapping is simply not secure. This is because and it is not secure in the sense that the resultant 128 bit strings that sender and receiver that they are going to derive are not uniformly random 128 bit strings. This is because if you see the ASCII representation of the letters for the uppercase letters A to Z, then all those ASCII representation starts with 010 as the prefix. So, the ASCII representation of A starts with 010 and so is the ASCII representation of B and so is the ASCII representation of Z and so on. So, it does not matter what exactly are the first 16 characters of the password M that is available with the sender and the receiver. If they convert the first 16 characters into their ASCII representation, then an adversary who knows that sender and receiver are basically taking the ASCII representation of the first 16 characters of the common password, the adversary knows that 37.5% of the resultant key are fixed and known to any third party. So, that means out of the 128 bit keys that sender and receiver has derived, 37.5% of the keys bits of the keys is already known to any third party in the world. And that is why we cannot claim that the resultant 128 bit key is a uniformly random 128 bit key. So, now you can see that we cannot just apply ad hoc mapping to highly unpredictable pre-shared data and hope that the resultant mapping gives us a uniformly random key. So, that is the goal of key derivation function. So, key derivation function, as the name suggests, it derives key from an already existing pre-shared highly unpredictable data, and what we do basically in the key derivation function is we can design key derivation function in varieties of ways, but what we are going to see is the highly practical instantiations of key derivation functions based on hash functions. So, the idea here is imagine that S and R have some pre-shared highly unpredictable data. So, till now I was just giving you an informal description of what we mean by pre-shared highly unpredictable data. So, let us formally define it. So, I say that it is highly unpredictable in the sense that it belongs to a probability distribution fancy X with big L bits of min entropy. What exactly that means? Well, that means that if I pick any value little x as per this probability distribution fancy X, if I pick a value as per the probability distribution fancy X, then the probability that the picked value is some given little x is upper bounded by 2 to the power minus L. That is what is the interpretation of this notation. So, this means that I am picking some value from the as per the probability distribution and the picked value is some random value. So, that is why this big X is the random value denoting the value that I am picking as per the probability distribution fancy X. And now I am arguing that what is the probability that that random value takes the value equal to little x for a given fixed x. If that probability is upper bounded by 2 to the power minus L, then I say that this probability distribution fancy X has big L bits of minimum entropy. Informally, what it means is that even the most likely outcome as per this probability distribution fancy X can occur with probability at most 1 over 2 to the power big L. So, what basically this L bits of min entropy captures it captures the probability with which an adversary can guess a value picked by a sender or a receiver as per the probability distribution fancy X. That means, if adversary already knows that certain outcomes are more likely to occur and certain values are less likely to occur from the viewpoint, and if the adversary strategy is to always guess that it is the most likely value that a sender has picked, then even in that case the probability that adversary's guess is correct is 1 over 2 to the power L. That is the idea of this notion of L bits of min entropy, right. So, assume both sender and receiver have access to a publicly known hash function, right, and they have some pre-shared data M which has L bits of min entropy. Then to derive a key, what basically sender and receiver can do is they can just evaluate the hash function on the pre-shared data M, and the resultant output, which I denote as K, will be the pre-shared binary string of size little l bits, which will be now available to the sender and the receiver. So, that is a key derivation function in its most simplest form. And now we can argue that if we model the function h as a random oracle, and if we take this construction and instantiate it in the random oracle model, and if the value of big L is sufficiently large, then the resultant output little k is indeed a uniformly random little l bit string from the viewpoint of any polytime adversary. And this is because of the fact, imagine there is an adversary A sitting between the sender and the receiver, and since we are now in the random oracle model, what the adversary is going to do is, adversary will be now making polynomial number of oracle queries to this h, and adversary won't be knowing what exactly is the underlying oracle h. So until and unless adversary does not query this oracle h on the exact value m which is pre-shared between the sender and the receiver, the value of k which sender and receiver are outputting here will be uniformly random from the viewpoint of the adversary. Now what is the probability that adversary indeed has queried for h of m, given that it has made q number of queries to the oracle? Well, if my probability distribution, or if the data m which has been pre-shared between the sender and receiver has big L bits of mean entropy, then what the adversary can hope for is that every time it can ask the value of this h oracle on the most favorable data that it feels that the sender and the receiver might have picked as per this probability distribution. So the probability that in each single query it has actually queried for the exact m is 1 over 2 to the power L, because that has come from the definition of L bits of mean entropy, and since the adversary has done q number of queries with maximum this much probability, adversary A might have queried for the input h m for the from the oracle h, and if we assume that big L is sufficiently large and if q is anyhow polynomially bounded in the security parameter, this is some negligible function in the security parameter. So since adversary has not queried for h of m except with negligible probability, from the viewpoint of the adversary the resultant key k is going to be a uniformly random L bit string, and that ensures that now sender and receiver can safely use the derived key k for any cryptographic primitive as the key. Say for instance, if they want to use the key k as the key for AES, they can safely use it. So now you can see that how this highly efficient key derivation function based on hash function can be proved secure if we go in the random oracle model, but if we just go in the standard model and use the standard properties of the hash functions, namely collision resistance, we cannot prove that the so called key derivation function is indeed a secure key derivation function. So that brings me to the end of this lecture. Just to summarize, in this lecture we have continued our discussion on the random oracle model. We have seen that we have certain arguments in the favor of random oracle model, we have certain arguments against random oracle model, and so on, and we have seen an instantiation of two important cryptographic constructions or primitive, namely commitment schemes and key derivation functions based on hash functions, whose proof we can give only in the random oracle model. Thank you.